Now generalization. Okay, I'll take few minutes to go for generalization. Also generalization, I will leave it to you, but I will give you the key how to start to generalize your problems. For example, if you go direct in generalization to beams, for example, I will give the keys. Beams, sorry, I use this. It's much better. I use blue one, much better. In beams, when we have beam, now your beam, this is your beam in bending, and this is x. So you have here f of x, and this is x equal 0, and this is x equal L. Now you have deflection at any point x. You will have w of x. This is a deflection. And you have theta of x. This is slope. And this is equal dw of x by dx. And you have bending moment, m of x. This is bending moment, which is equal ei. This is the moment of inertia times second derivative dw of x by dx square. And you have shear force v of x, which is shear, which is equal to ei times d3w by dx cube. The positive directions is straightforward. If this is a beam and the beam is going to rotate like this, so this is w positive and this is theta positive. And as far as these two, this w and theta are functions, and m and v are stress resultants. Stress resultants. Stress resultants means it is integration of stress over the cross section. So when we integrate the stress over the cross section, that means we are integrating tensor. And when we have tensor, we have no sign. Because of that, it is a convention. Because of this, we have the following convention, which is positive directions. This is V, the positive direction. This is the positive direction for V and M. When we have this end, and when we have this end, we have V positive in this direction, and the moment is positive in this direction. The differential equation for the beam, it is EI times D4W by dx4 plus f of x equal to 0. It is the same like bars. It is the same like bars, but with force derivative. So you expect to have 4-time integration, but it is the same. It is exactly the same. And you have different boundary conditions. For example, if you have free boundary conditions, that means V equal to 0. Or if we have something like force or something like that, and M equal to 0. So every boundary condition, now you have 2 boundary conditions instead of 1. Okay? If you have, for example, clamped boundary condition. When you have clamped boundary conditions, that means theta equal to 0 and deflection equal to 0. And so on. You can have guided boundary condition, something like this. You have a lot of stuff. You can generate your boundary condition. I'm just giving you the key, how to solve this problem. If you are interested, I can send you a lot of things I have. Okay, actually I teach this one in third level in structural engineering. You will find yourself using these boundary conditions. You are able to solve any type of beam, In order to solve any type of beam, I'm just to solve, just give a hint to solve any beam shape. You will be able, for example, if this is a beam, you will have the concentrated force. You will put the concentrated force using Dirac delta. The support, you will put the support using unknown times the Dirac delta. Okay, distributed load, you can generate distributed load like this using Heaviside function, using the sine function, sine something minus something. Okay, try to build up a general beam, but you are able. I have done it. You are able to solve this one, and you don't need any type of structure analysis programs or anything. Just go with the basic differential equation. Also, you can use complementary solution and particular integral. You can use the same idea of complementary solution and particular integral in beams. It's the same, okay? But with boundary elements, for me, bar is enough. The idea of the bar itself is enough. The idea of complementary solution and particular integral is enough to be understood on bars. This is enough for me. The last thing I want to talk about it will take something like 5 minutes or something like this, which is if I have pile element. If I have pile element or something like this. This is what we call it, pile element. In pile element, you will have, it is like bar, it is bar plus friction. It is like piles inside ground. For example, this is your bar, and the friction here distributed all over the shaft of the pile. But the problem here is the friction is equal to the unknown displacement times coefficient, we call it K. This is known coefficient, but the displacement is unknown. Because of that, your differential equation now is EA like bar times D2U of x by dx squared plus P of x. It is exactly like bar. But in the same time, you have additional domain load, unknown domain load, which is equal minus K times U of x times K minus U of x equal to 0. The problem here, this is unknown and this is unknown. So you will not be able to generate the solution of this problem by integration. Okay, for example, if this one, you are going to say this one part is P and this one is A or something like that. Let me generalize it using the same notes I have here. So it is d2u of x by dx squared minus k over ea times u of x equal p over ea. This part we'll call it A and this part we'll call it B. You can have the general solution by guessing. Let me tell you something. The solution of the differential equation, it is either by integration, separable, and by integration or using integrating factor or anything like this, or using guessing like undetermined coefficients or anything, but it is guessing at the end of the day. Or using integral transform, using Laplace transform or any kind of integral. You don't have a third method. Okay? So the general solution u of x, you can guess it, equal minus b over a plus e over square root of a times x. You can use Mathematica to generate this one using minus square root of a times x plus c2, and these are the two constants. You obtain them from the boundary condition, and this part is a particular integral. This is a particular solution. These are the particular solution. Why I insist on giving this problem? Why I insist on giving this problem as key? I'm leaving to you beams. You can do it by yourself. It has nothing to add. It has nothing to add to. It has nothing to add to boundary elements. Actually, to re-demonstrate the same idea on beams, but here I'm insisting on putting this pile element mainly because when we go to bar dynamics and using time differencing or Laplace transform, we'll end up to the same equation like this one. We'll end up to the same equation like this one. But instead of this part, like friction or something like that, we'll have the inertia terms. So this element is very, very important to be studied. Okay. Up to now, I may say I finished my talk today. I covered the bars. I covered the complementary solution and particular integrals. I generalized it directly to beams and pile element. If you are interested, I can present a lecture for beams and piles and all of this, but it has nothing new to do within the context of the boundary. We care about the boundary element itself. We don't care about the structural mechanics problem itself. Okay. Next time I'm going to talk about the indirect form for bars, and I'm going to talk about the direct form for bars. We will put the first stone actually in the boundary element big wall using direct formulation and indirect formulation at the same time. Thank you for listening. At the moment, I will stop recording now here.